Howdy AP Calculus BC. You've now finished 2/3 of this topic where we began with parametrics. I did a bunch of practice with those, a short little unit on vectors, and we're finishing this with polar. I argued that polar is probably most prevalent out of these three. However, you do need to know all of them, and some form of all of them will show up at some point. We are going to begin polar the same way we began our other two pieces, without calculus. And in fact, I think the first 2 days are going to be without calculus because we have the time, and it really does help understand, or help you understand when we get to the calculus part of this, if you have a better understanding of polar. In particular, polar graphs. The equations are fun, and you get to play around with them and see the connections to our Cartesian or our rectangular coordinates, but we really need a good foundation in polar graphs. Now, you've actually done this unit before, or parts of this unit if you took trig with me, but if you haven't, or you've forgotten because it was probably about 2 years ago, it's definitely worth doing again. So the first thing we're going to do is just graph a whole bunch of different polar graphs. And although you might not be able to understand, or you might not understand why the graphs look like this at this point, you could still probably by the end of the lesson today recreate a similar style graph just by using leaps of logic. So we have 4 different types of graphs. 1, 2, part 3 and 4 kind of go together, and then this last part is really just a bonus. But up through part 4 are types of graphs that you can potentially see on the AP exam, though usually they let you have a calculator on those. And then part 5 are just fun bonus ones. So let's begin. You need to go ahead and put your calculator in polar mode, and to remind you what that looks like, I'll show you each calculator right here. Our first one, we're just going to go to the home screen, then to graph, and currently we're in function mode, f of x. To put this into polar, we just go to graph entry edit, and by the way, that's how we switch it back to function mode. We just pick 1. So if anything ever goes wrong in your calculator, just go graph entry edit 1 for a function, and your graphing screen will look like it should. And then we're going to go down to polar, and click, and great, now we're in polar mode. Polar is always given as r is a function of theta, so r of theta, which means our input is going to be theta. Yep, nothing bad there. And then we should also probably look at the 84 since that calculator is still common. And we need to just go to mode, and we're going to our last of 4 modes on here. We've done functions, we've done parametrics, we've done sequential, and we're picking polar. Also, you have 2 of these, radians and degrees. We want to be in radians in both. Calculus is rad. There's no reason your calculator should be out of this unless you're doing physics. So we have both of those. When you hit y equals, you'll see r equals, and now our button over here, function, parametric, polar, sequential, so we're in polar, is going to give you theta when you click it. Very exciting. Alrighty, this is going to take you probably about 20 or 30 minutes or so to do. I'm going to do it a little bit faster, and I won't go through all of them. So you will want to have gone through all of them, especially because that's going to help you make up your own rules on how you can graph each of these without a calculator, which is one of our goals by the end of this. So go ahead and pause me. You're going to do both pages, and then once you unpause, we're going to run through some of them and discuss some names that you should know, how you could create them, all those fun things. Ready, set, go. Alrighty, and we are back. Let's go ahead and run through these. The first one is not bad at all, right? Part 1. It says describe the graphs in part 1. Hopefully you came up with circles every time. If your circles looked smushed on your calculator, and I'm sure that's a very technical word, it might be because your calculator window is not square, right? For example, this axis goes up to 10. These ones only go up to 6.65. Very random number. There's a reason behind it, but still random. So if I were to graph something like 2, let's go cosine of theta. Where do we get theta? Well, I think it's hiding with the pi down here, isn't it? Yep, there it is. 2 cosine of theta, like so. First, we should understand it's a circle, and hopefully you've seen that these circles with cosine are along the x-axis. Think back to your unit circle. And with sine are along the y. So I'm going to go ahead and hit enter, and we see that actually does look like a perfect circle. That's very nice. However, if it didn't, sometimes you can see this a little bit more cleanly if you try a different zoom, especially on the 84, and you're going to try a zoom square, and that's going to, that was weird, and it's going to generally give you a better picture here. So zoom square if you want to see it a little bit more accurately, but the Inspire does this pretty well. Great. So circles, and you can really come up with your own rules with these. Cosine along the x-axis, this number in front is telling us our diameter, right? If it's a 3, it's going to look something like that. So the center is here, and we have a full diameter of 3. You might also notice that if there's a negative, it's just going to flip it over to the negative side of the x-axis. You can also laugh at my beautiful circles here. And of course, sine does the same thing, but puts it along the y-axis or the negative part of the y-axis. Easy enough. Make up a generic name. Well, it's the same as the actual name. These are circles. Great. Very exciting. We may not know why or how they're created, but that's an easy equation of a circle. Let's go ahead and move down to part 2. This one is a little bit different. You'll notice that there are 3 types of graphs here. And the 3 types of graphs are all known as, and here is your buzzword for today, or your new word for today, as limicons. And has that cool C with the little guy underneath, right? Limicons. And there are 3 types of limicons that you'll see here. You will see a limicon with an inner loop, a limicon without an inner loop, and you will also see a cardioid. So really 3 pieces here, and we'll look at all 3 in just a second. So you have one that has an inner loop, no inner loop, and a cardioid. Alrighty, I have these prepared for you on Desmos. Again, we're not going to look at all of them, and I'm going to try to pick the right screen at some point. There we go. Here's my limicon folder that I created ahead of time, and we're going to look at what happens when the 2 values, the value multiplying by the trig function, right? This piece right here, 2 cosine of theta is just a circle, but then adding to the trig function are the same number. If they are the same number, they make a shape known as a cardioid. Why a cardioid? Well, hopefully you can see our word for heart in there, right? Cardio, cardiologist, and it does look like a heart. Very exciting. What happens when the number adding is smaller than the number multiplying? Well, this gives us our limicon with an inner loop. And you can see we have an outer loop and then our nice little inner loop along the inside. And last but not least, what happens if the number adding is larger than the one multiplying? There's an invisible 1 here. This gives us a limicon without an inner loop. So with an inner loop, without an inner loop, and when they are equal to each other, a cardioid. Why do they do that? Well, that's actually going to be a really big focus, especially the one with the inner loop. We're going to spend almost a full class discussing those inner loops right there. So make sure that you are comfortable with the differences, but you don't have to be perfect with it. Maybe it's just an idea that they exist until we study them later on. All right, second page. Graphs from part 3 and part 4 are both known as rose graphs or sometimes rose petal graphs, which is kind of interesting because to me they don't really look like roses. But either way, the focus I think is on the petals here, and you can call them whatever sort of flower petal graph you would like. You'll notice that there are a couple differences here. Right, you might be tempted to look at this first guy and say, oh, 2 cosine of 3 theta. And when you graph that, and again, I think I have this prepared for you over here. When you graph these roses and you do 2 cosine of 3 theta, you say, oh, that's exciting. There's a 3 here, and I notice 1, 2, 3 petals. And there's a 2, and you might notice that the length of the petal is 1, 2. And that works perfectly. And you said, okay, well, that's cool. So now if I do 2 cosine of 2 theta, I should have petals that are a length of 2. And there should be 2 of them. And when you click that one, you'll notice you're almost right. The petals do have a length of 2, but there are 4 of them. And so you might start to draw a conclusion that anytime the value inside, right, this 2 that's right here, anytime the value inside the parentheses is even, you see double the number of petals. And anytime the number inside is odd, you see exactly that number of petals, and you wouldn't be wrong. Now, there is more to it than that. And notice I said C and not that there are. And you also might notice that on the restrictions that Desmos adds automatically, this one goes from 0 to pi, and I deleted it. This one goes 0 to 2 pi. And why would that change? Well, we are going to, again, focus another class on these rose petal graphs to have a better understanding of what happens with them. Okay. Moving through to our last part, we have part 5. Part 5 are just the cool different graphs. Now, you might notice that most calculators, including Desmos, I think, will not graph these. This would be equivalent to graphing, and it's not the same, but to graphing y squared equals 4 cosine of 2x. And most calculators don't like to graph an equation unless it's in the form of y equals. So how do you get it in the form of y equals? Well, of course, you take the square root. You say r equals the square root of 4 cosine of 2 theta. And if you wanted to simplify further, you could say it's 2 times the square root of cosine of 2 theta. And then some of you might remember, too, that we introduced a square root. And you might say, well, do we need a plus minus in front here? Do we need both of these? And I mean, to be safe, you should put it. But let's see what happens when we graph that. You also might remember that you can not actually graph an equation on your calculator with plus minus. Look, I've got a little exclamation mark. Desmos is saying, I don't like this, so I'm going to get rid of it for now. So I have the positive version. We can't graph plus minus at the same time. It means two different equations. So we graph the positive version and get this cool little infinity sign. Very exciting. These fall under the category of lemniscates. Right? And I'm sorry, I didn't go into the vocabulary earlier, but limousin is actually French for snail. And it is different than escargot, which also has to do with snails in French food. But either way, you can look them up. Limousin, French for snail. So lemniscates are these cool infinity signs. Now, here's the one with a positive 2. Here's the one with a negative 2. And they actually look identical. And one thing with polar graphs that I actually quite enjoy is usually introducing a negative or a positive in terms of multiplication doesn't change the graph. It doesn't have that reflective property that it does with our usual rectangular coordinates, where rectangular is defined as x and y and polar is defined as r and theta. So we actually don't need the plus minus here. It's not bad to put it. You're just double tracing the graph, but we really only do need one of them. You'll notice that cosine, again, is along the x-axis. Sine is a little bit different, though. I think sine is not going to be along the y-axis. In fact, it only turns diagonally, kind of 45 degrees up. And so I did pose a challenge for you, and the challenge was, what could you do to make the infinity sign symmetric about the y-axis? How could you create that graph using polar? And you guys should post and let me know if you figure it out, because it is pretty tricky, I think. All right, last one, r equals theta. R equals theta is a cool graph. It is generally known as Archimedes' spiral. And when we graph this, you see a little swirl, and you're like, well, that's pretty cool. But then if you zoom out, it keeps going and keeps going. And, oh, it stopped there. That's exciting. Well, it only stopped there because we stopped at 12 pi. If you increase this to 14 pi or 24 pi or whatever, this will go forever and ever and ever. The fact that it's known as Archimedes' spiral means that this was a commonly known graph all the way back to the Greek times. Yeah, so polar's been around for a long time, and it's actually very sensical. Our XY coordinate plane has been around for much less time. That was our René Descartes there, right? His Cartesian coordinates, and that was much, much, much later than the Greek times of Archimedes. So we have this polar stuff. I did want to take a quick second and show you some other cool polar graphs, because it is, I think, much easier to do neat shapes with polar graphs than it is with our Cartesian coordinates, our rectangular coordinates. So our other polar graphs that I have for you are some cool ones. So I'll pick this first one, and most of these have cool names too, but I won't run through all of them with you. But this first one, you're like, well, that's kind of cool, but then if you zoom out, it's actually quite neat, right? This is a graph that comes in, runs over itself, but then has a second little hump kind of going up here. And you'll notice that they never come back on each other. They're almost two completely separate graphs. It's a pretty cool one. This next one, you're like, well, there's nothing there, but if I hit the home button, This one is just wild looking, isn't it? It's like a flower inside of a flower inside of a flower, or maybe a frog. I'm not sure what you quite see sitting there. Or this one, remember r equals theta was our Archimedes spiral. If we look at this, you're like, well, that's a straight line. That's kind of boring. Oh, it's kind of like that Archimedes spiral again. But notice as I go in further and further and further, it just spirals in on itself and gets closer and closer. This is like an unfolding spiral, or maybe like a fern, right? You see those ferns that wrap in on itself? Okay, looking at a few others. This one's kind of cool. If we hit that home, right, we just have, kind of this circle that doubles into itself, kind of like a limison with two inner loops. Okay. Last one, we look at this guy, and this one, I actually remember the name. This one is known as Oscar's butterfly. So if you look at it, I think it's kind of cool. You have these wings on the outside. It almost looks like a dragonfly in on the middle. But long story short, really cool graphs with polar, but we haven't answered the overall question. And our question to ponder here is, why do the polar graphs look the way they do? Or maybe a better way to phrase that is, how are polar graphs created? And we're going to start to answer that question today, and we'll deepen our knowledge over the next 3 or so classes. Okay? Rectangular Cartesian coordinates are in the form of x, y, where it's kind of weird because in this equation we say y is a function of x, right? Y is the output, x is the input, so the input's on the left, the output's on the right. And of course, x is the movement on the x-axis. You move some amount this way, and then y tells you to move another amount this way, and you get a point. Polar coordinates are extremely confusingly, in my mind, written in the form r comma theta. And that's confusing to me because this is r equals a function of theta. So strangely, theta is the input, kind of like our x here, though it serves a completely different purpose, and then r is the output. And I don't like that. I don't really care which way they go, but I don't like that one is the input, one's the output, and then the other set switches them. But I'm sure there's a reason, I just haven't come across it. Either way, good to know. You will not be confused about which one is which, though, because theta almost always is going to be written in radians, and r is almost always not going to have radians, and we'll show you how to use those in just a second. Now, how does this work? Well, let's do a nice example right here. We have the point 4 comma 2 pi over 3, and there are 2 ways to find where this point is located. What we have to the right is a polar grid. Now, this polar grid is also an xy axis. And to see the xy axis, we just find the origin, and we can see that really right here we have a y-axis and, of course, an x-axis. So don't lose sight that there are really 2 ways to find the same point. In this case, though, we're going to find it the polar way. The first way to find it using the polar way is to start with r. So we know r is 4. How do we use that? Well, we jump down here, and everything in polar starts with the origin. And I'm going to go out 4 marks. So we have 1, 2, 3, 4. And those are the same tick marks on an xy axis. So it would be 1, 2, 3, 4. So with polar, we go out 4. And you may want to hold off writing this because I'm going to erase pieces of this as we go through. And then we rotate 2 pi over 3 counterclockwise, just like normal trig. So right now I'm here, and I need to rotate 2 pi over 3, an angle of 2 pi over 3, which we see is right here. And so our final point of A is located right there. Right? Nothing too terrible. The weird part with polar coordinates, though, is there are an infinite number of ways to get to the same point. In rectangular coordinates, there are not. There is only one unique set of coordinates that will get you there. But to illustrate this, let's look at a point that will get us in the same spot of A. And let's keep the length of 4. So let's keep going out 1, 2, 3, 4 here. But then let's just rotate backwards. And to rotate backwards, you might remember we give our theta a negative coordinate. And to go backwards, this is going to be 1 pi. I should do better than that. This is going to be 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. So I can do negative 4 pi over 3 and get to the exact same location. Negatives just rotate us backwards. Awesome. So that's a second way to get to A, and that is in fact what they've asked you to do here. So why don't, let's just go through the rest of these. You'll get a chance to practice. I should give you a second way to do this because some people, namely me, enjoy that because 7 pi over 6 will be the input in our equation, that we could rotate first. How does that work? Well, 7 pi over 6 is rotated, and I'm just going to keep it nice and short here, is rotated over here. And then we extend out 3. So we go 1, 2, 3, and that is where our next coordinate lies. And this would be the coordinate for B. So whether you rotate first, then go out r, or go out a distance of r and then rotate the other way, that's fine. Either way works. You might start to realize too that r, I like to think of, is the radius of a circle, hence r. All right, is there another way to get there? Well, of course there is. I don't think I mentioned, though, what we do with a negative r, so that's probably worth talking about as well. Negative r, a negative radius, would mean that instead of extending out in the direction that you're pointing, negative r would mean start that way, but point the other direction. So for example, if I wanted to get here, I'm going to do the rotation first and then r. You'll notice that this is completely opposite of pi over 6. So why don't we rotate to pi over 6 first, just right here, and then instead of extending out in the pi over 6 direction, 3, let's extend to negative 3. So we're right along this line, and instead of moving in the positive direction, we are going to move 1, 2, 3, and negative 3 will get us to the same spot. So to recap, positive rotations counterclockwise, negative rotations clockwise, positive values of r move in the direction that you're rotating, negative values of r move you in the opposite direction of where you're facing. I think that probably gives you enough to graph C and D. Once you've graphed those two, unpause and we'll make sure that you're in the right spot. Ready, set, go. All right, and you're back with us. C, a couple ways to think about it. We're going to 5 pi over 4. 5 pi over 4, let's see, pi's over 4, those not even on here? So we have pi over 4 right here, right? That splits this into 2 equal degrees. So here's pi over 4, 2 pi over 4. This one's got to be 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi, and 7 pi over 4. Nice. So we're going to spin to 5 pi over 4 right here. But instead of our r value moving us out, nope, didn't go far enough, right here, there we go, kind of hard to see. Instead of our r value going out in the direction of 5 pi over 4, because r is negative 2, we're going to go out 1, 2 in the opposite direction and end up on pi over 4. And I imagine you can find a similar coordinate there, right? It's a pretty quick one. And then part D. Part D tells us to spin negative pi over 6 this time, or we could go the other way. Tells us to go out a direction of 2, and then spin negative pi over 6, which is 11 pi over 6. And that gives us our answer of D. So this would be, another way to put it, is to 11 pi over 6. Nice. We're almost done with this. The only thing we need to conclude with today is how to convert between rectangular and polar coordinates from one to the other and then back again. Because I mentioned that this is still an xy coordinate plane. And so if we were able to get there by spinning, we should also be able to get there using our xy directions. Yeah? So for example, if I wanted to approximate the location of point C right here, it looks to me like you'd go maybe over 1.5-ish and then up. Also looks like 1.5-ish. So would this point also be called 1.5 comma 1.5 in an xy coordinate plane? Well, maybe, but that could also be an approximation. There's probably a better way to do it than guessing. So we're going to go ahead and jump down to the last bit. Now, some people look at polar coordinates and go, well, why do we ever want to do this? I mean, we've done x, y our entire life. It seems kind of silly that we would switch it up now. And although you do have a fair point, polar coordinates are really, really useful. In fact, I bet you use polar coordinates more in your life than you use rectangular coordinates. Think about when you use rectangular coordinates. You might use them if you're like walking along a city block and you need to go exactly one direction then up another direction. It's much harder to just turn and then try to walk through a building diagonally. You might use them when you're driving too, but polar for probably everything else, right? If you're, let's just use the walking example again. If you're walking in the middle of a field and you see someone you want to talk to, you don't walk sideways. Like you don't, let's see, I should draw a picture, huh? So if you are here and you see somebody over here in a field, you don't walk horizontally and then walk vertically to get there. You just turn to face them and then walk across the field, and that is polar. In fact, you see polar a lot. You should even recognize this grid as our grids that we use for radar, right? Radar definitely uses polar signals to turn to where they are getting their sound bounced back to, and then use a radius to approximate how far away that thing is. All right, so let's go ahead and start converting these. Everything with polar has to do with right triangles. Yeah? If we place a point at the tip of a right triangle, there are two ways that we can get there. You can rotate theta and then go out r, or you can start from the origin and you can go over x and up y. And putting those together creates a right triangle. Well, let's derive some relationships from this right triangle. In particular, if I took cosine of the angle that we rotate, we should remember SOHCAHTOA, right? I'll write it out in case we have forgotten. SOHCAHTOA, and I always write it like this so that you can see the fractions in there. Right sine is the opposite divided by the hypotenuse. We're into cosine on this one, though, and cosine of theta is going to be the adjacent divided by the hypotenuse. Our adjacent side here is, of course, x, and our hypotenuse is r. And so if we wanted to not write this as a fraction, then I think we could probably multiply both sides by r here, and you can show this or not, totally your choice, but that's going to give us that x, the x coordinate, is found by multiplying r times our cosine of theta. Sine of theta is very similar. That's the opposite over the hypotenuse this time, right? Opposite is over there. And we can again multiply both sides by r to isolate, just get rid of that fraction, and it gives us the commonly used relationship that y is r times the sine of theta. No real surprises here, though, because x has always gone with cosine for our trigonometry and y has always gone with sine. We're just adding r there to move it off of a unit circle. If you don't have r, if there's just an invisible 1, you get your unit circle relationship. Putting r lets us move beyond just having a length of 1 in every direction. We also, of course, have the Pythagorean theorem, x squared plus y squared equals r squared. If you wanted to isolate r, you could, of course, square root both sides, but we know we can't distribute. The square root kills puppies. That's my background meme, and that's no good. Last but not least, we can also divide y over x, and this one is a little bit trickier here. If you divide y over x, you might realize that you're really doing the adjacent over the opposite over the adjacent, and so that is tangent. How do we create that? We do tangent of theta. And although you can do this, I don't suggest it. You can isolate theta on both sides by taking the inverse tangent, right? And so we could say that the inverse tangent, or the arctangent, of y over x is theta. The reason I don't suggest that, though, is because inverse tangent is restricted to 2 quadrants, right? It's only going to give you answers here and here. So if you rotate further, you have to add 180, or if you rotate backwards, it won't give you an answer. So things get a little bit weird there, and we'll have to bring in some more trig knowledge. But again, this is just a really good, deep dive into this, and my guess is you probably will not be asked to do this too often. So here we go. 2 practice problems, and then we're done. Convert 2, 5 pi over 6 to rectangular coordinates. Then graph both the polar and rectangular coordinates to check your work. I'm actually going to go backwards here. I like graphing these first and seeing if we can figure out how to do it without having to memorize the formulas up above. You will definitely need these guys at some point, but let's see if we understand what's happening. 2, 5 pi over 6. So 5 pi over 6 is our line out here. 2 means go out 2 and then rotate to 5 pi over 6, so 1, 2. Here is our point. Okay. Now, one way again to write that point is 2, 5 pi over 6. However, we want to see if we can get there using rectangular coordinates, right? So for rectangular coordinates, I'm just putting tick marks here so we can approximate at least. It looks like we go -2, a little bit less than -2, and then up approximately 1, maybe a little bit more than 1. Well, how do we do it? I always draw my triangle. So the first thing is we're going to create the hypotenuse and then create the two sides. Okay, looks pretty good. We have an x, a y, and a theta. Our theta is going to be a little bit trickier here, so I'm actually going to go ahead and zoom back out and redraw my triangle just so we can see what's happening and I don't have to be so zoomed in. Here's my theta. Now, this theta is known as a reference angle in trig, right? My theta is not 5 pi over 6. The theta we want is just this little guy right here, right? And so this angle theta, hopefully we remember from trig, if this is 5 pi over 6, you need to go 1 more pi over 6. So theta is pi over 6 here. We also know the length of the radius. The length of the radius is 2. Okay, well, what can we do from here? This is actually a special right triangle, which makes things a little bit easier, but I'm going to kind of take you through this if you maybe didn't remember as a special right triangle and figure out how we'd get to the other pieces. Okay, so we have x and we have y here. Of course, x standing for the x coordinate, y standing for the y. How do we do it? Well, we just need combinations of trigonometry that relate two sides together. In particular, if I wanted to find the x first, I'll use a little room over here, then we need to find a way to relate x and two things we know. In particular, I think if we're going to relate those, we know an adjacent and a hypotenuse. So we're probably going to realize, hopefully, that that is cosine. And so we're going to say x. Oh, okay, so, and maybe I should do it this way. We're going to say cosine of pi over 6 equals, right? And then it's going to be the adjacent over the hypotenuse, yeah? And then we can multiply both sides by 2. And then finish this off and say, oh, okay, I remember my trigonometry, I hope. Cosine of pi over 6, 30, 60, 90. Let's see, it's across the third. I think that's going to be square root of 3 over 2, which is just square root of 3. Now, looking at this, you might realize that that's not going to give us the right answer because square root of 3, if we are thinking about this point over here in terms of an x comma a y, square root of 3, that's the x we just found, would move us in the x direction, and that's the wrong way. So we do need a negative. So what you'll see instead of people using this reference triangle like I just drew, or this reference angle, is they'll use the actual angle of rotation. So the other way that's much more common is they use our formula, x equals r times the cosine of theta, where theta is the actual rotation. So that gives us r, which was 2, times the cosine of 5 pi over 6. And simplifying this down, that does become negative root 3 over 2, which is negative root 3. Let's do the same thing with y, but let's use the faster method. So with y, we know that y is equal to our cosine, our sine of theta. Y and sine are pretty well linked here. And we knew that r again is 2, and our angle of rotation, 5 pi over 6. Sine is positive in the second quadrant, think positive y-axis. So we have 2, and then if cosine was root 3 over 2, then I think sine has to be 1/2, doesn't it? And so we get 1. So then the question we have to ask is, does that make sense? If I go negative root 3, remember square root of 4 is 2, so it's a little bit smaller than 2, and that is a little bit smaller than 2, and then we go up 1, and that does look like it's up 1, do we get to that point? And yes, yes we do. All right, working backwards. Convert 3, negative 3 to polar coordinates, then graph each of them. We'll again do it backwards. We'll graph this first. 3, negative 3. So tick marks first, 1, 2, 3, comma, negative 1, 2, 3, puts our point right about here-ish, give or take. It looks like it landed right on 7 pi over 4. It could be close, though. Again, poor artistic skills. All right, how do we do this? We make our right triangle. So let's go ahead and draw our hypotenuse, and then we'll, yeah, you'll see I'm not even going to line up perfectly there, so That's fine. There we go, something like this. And then we have our guy right here. What else do we know? We know this is 3, this is -3, so I'm ready to redraw my triangle over here just so we have a little bit more room. Draw the triangle a little bit larger. We know that this is 3, this is -3, and then there are two things we don't know. We don't know r, and we don't know theta. All right, two ways to do this, and I'll show you with a calculator as well. I think it's important. To find r, that's pretty easy. Pythagorean theorem, right? So we're just going to go 3 squared plus -3 squared equals r squared. 9 and 9, so 18. Taking the square root of each side, realizing that 18 is 9 times 2. That gives us 3 root 2 for r. Nice. But what about theta? A couple ways to do this. Option number 1 is the easiest, and it involves you knowing your right triangles. You go, oh, those are the same value, therefore this must be a 45, 45, 90 triangle, which means that we just had to rotate backwards. So I think theta in this case is -45 degrees. You could also make the argument that you rotated the other way, and you could say it's negative whatever that is. I never remember those. I'd have to probably go to pi over 4s instead. And I know going the other way, that would be 7 pi over 4, right? Because that would give us 1 pi over 4, 2, 3, 4, 5, 6, 7 pi over 4. Yeah, we could go that way too. Either one of those is acceptable. But what if you don't recognize it's a special right triangle? What if you want to use one of our formulas? Well, one of our formulas says that if we do the opposite, right, -3 over the adjacent over 3, then that is equivalent to tangent of our unknown theta, right? We're pretending we don't know theta right now. So this tells us that -1 equals the tangent of theta. And I always suggest that you, again, use your special right triangles to solve this. So maybe treating tangent as sine over cosine and thinking, well, when does sine over cosine become 1? Well, it's when they're at the same rotation. And hopefully now you go, oh, they're at the same rotation at multiples of pi over 4. But if you don't remember that, then you can always go one step further and you can try that inverse tangent. And so when you do inverse tangent on both sides, and I'll use the arctan notation, just so we've seen both today, you get this, inverse tangent of -1. Okay, now showing this to you on a calculator really quickly, let's just go ahead and use this guy since I have it open. Okay, we're going to use the inverse tangent, and they use the -1 notation here of -1. We hit enter, and my calculator will tell you -pi over 4 because it's a CAS calculator. Most calculators would not, and most calculators would give you this guy. And that guy's never going to be an answer choice, so that's going to be a little bit trickier. You might realize that that's pretty close to 3 divided by 4.75, so I go, maybe -pi over 4, but what if it's not exact? And here's the other fun thing, right? What if this triangle right here, instead of being located in the 4th quadrant, what if this triangle was located up here? Oof, that was not good. So we had 1, 2, 3, 1, 2, 3, right around here. What if this was your triangle? And now we would have -3 and 3, and isn't that the same triangle? And if you wanted to find theta, you would still put these on top of each other, and you'd find tangent of -1. And now it's just plain wrong. In this first case, you'd get the right answer, -pi over 4. If it's not correct, though, don't forget that tangent will only give you answers in these 2 quadrants. So if it gives you an answer in this quadrant, and you're like, whoa, I want this quadrant, what do? You either add or subtract 180 degrees, or you can add or subtract pi. So if you want, where you say inverse tangent of theta is in the wrong, and I'll put air quotes here, wrong quadrant, then add or subtract pi or 180 degrees. And that will move your answer into the correct quadrant. Again, I'm not sure that any of this would ever happen. This is mostly trig knowledge, but we do need a good background in trig to understand polar graphs. Okay, there's a little bit of practice here for you. As always, I will have the answers posted on Teams or wherever we're posting these days. So let me know if you have any questions. It should go pretty darn quickly for you. And thank you for sticking through. The rest of our lessons on polar will go much faster than this one, but I wanted to do it due diligence. So have a wonderful day and come back next class for a much faster video on just converting between polar and rectangular equations.